Всем привет. Сразу прошу прощения за столь дурацкие видео, потому что у меня дома все спят, и я разговаривать, объяснять не могу. Сегодня я пишу час или больше, посвященный ам, отладке в RTOS, либо дебагингу. Все тупо пишу как есть, чисто для себя. Будут вопросы, обращайтесь. Всем пока.
Hello, I'm Todd Mullenix, the RTOS Applications Manager at Texas. This presentation will cover common issues that occur in any application and show how RTOS can help you debug your application and resolve the issues quickly. The three main areas I'm going to focus on are stack overflows, device exceptions, and memory mismanagement. At the end, we'll use the techniques covered to help find three subtle errors in a simple application. But first, as everything on the web now, a 30-second commercial about RTOS. A common problem with any application, bare metal or one that uses an RTOS, is stack management. If you make the stack too big, you waste memory. If you make the stack too small, you might get stack overflow and potentially really bad things happen. Let's look at an example of stack overflow. Here, the function getInput has called update display. We see the normal things like parameters, return address, and local variables for the two functions on the stack. Let's see what happens when write_block is called. But there's a really big local variable called temp_buff in write_block. So we see the parameters go on. Now we see the return address, and now the locals. Boom. I really hope the motor control settings were not just messed up by the stack overflow. With RTOS, there are two types of stacks. The first is the system stack. All hardware and software interrupts share this stack. The size of the stack is determined by the program stack value in the RTOS configuration file. Each task has its own stack. This is needed since tasks do not run to completion like an interrupt does. Instead, they are generally in a big while loop, either running or blocked waiting for input or a resource. The size of the task stack is specified when the task is created. RTOS allows you to initialize both the system and task stacks with a known value. This is done via the task.init stack flag and the HWI init stack flag parameters in the RTOS configuration file. Enabling the stack initialization requires a small amount of code space, approximately 140 bytes. Enabling this feature allows the RTOS Object Viewer, also called ROV, in CCS and IR to show the peak usage for the system and task stacks. When the target is halted and you select a tab in ROV, ROV goes and reads the necessary memory off the target and displays the results. ROV does not add any footprint to the target. ROV has a really smart memory browser. Any characters that are in red denote that the value changed from the previous time. If it detects a problem, for example, a blown stack as we see here, it will display a red cell and an error message to help the developer find issues quickly. Being able to see the stack peaks allows the developers to save memory if the stacks are too big or find overflowed stacks quickly. One piece of advice: when you have the task detailed tab open, ROV is reading and analyzing potentially significant amounts of data. This may result in slow single stepping in the debugger. When single stepping, it's recommended to either close ROV, disable the automatic updating of ROV, or open a tab in ROV that updates quickly. For example, the task basic tab. There are two additional parameters in the RTOS configuration file: task.checkStackFlag and HWI.checkStackFlag. When the task.checkStackFlag is set to true, on every context switch, the previous running and new running task stacks are checked for overflow. If either stack is blown, an error is raised. Developers can plug in their own error message to act accordingly. When the HWI check stack flag is set to true, the system stack is checked in the idle task. This was done to minimize interrupt latency. Setting both of these parameters to false results in approximately a 290 byte footprint savings. We recommend developers enable both the stack initialization and runtime stack checking features during development. As the application becomes stable, they can be turned off if memory is a scarce resource. They can also be left in. In this case, it's recommended the developer plugs in an error handler that can gather any information for future debugging and then act accordingly. For example, reset the device. If you're using CCS, there's a nice trick to discover where the stack peak usage is. First, run the application, making sure to hit all the use cases. Halt the target and see what the stack peak is. In this case, 424 bytes is the peak, or also called a high water mark. Now create a hardware watch point at the stack base plus stack size minus peak address. Restart the application. Since you have stack initialization turned on, the watch point will be triggered when the stack is initialized to hex BE. Continue running the application and start exercising all the use cases. The next time the watch point is triggered, you can look at the call stack to see under what conditions you got into this state. Please note the quality of the call stack in the debug window is dependent upon the device, compiler options, and toolchain being used. In the CodeGen Tools package, there's a command line tool called CallGraph. This tool statically processes an out file and generates a worst-case stack usage table. This tool is useful in helping define poorly designed code from a stack usage perspective. Note, the tool does not analyze a running application, so there are some limitations. For example, it cannot see that a function is calling another function via function pointer. For example, I know that uart_write calls uart_msp432_write via function pointer. CallGraph cannot determine this. Additionally, assembly code needs to be instrumented to allow CallGraph to determine its count when determining the worst case stack usage. RTOS currently only has a very small amount of assembly, but it is not instrumented, so it is not counted in the worst case stack usage numbers in CallGraph. Another cute technique to catch stack overflow is to use the Memory Protection Unit module in RTOS, also called MPU. It is available for both Cortex-A and Cortex-M devices. Via the MPU module, a developer can configure a small no-access block at the top of a stack. Then if the stack is blown, an exception will occur. Let's turn our attention now to device exceptions. What is an exception? Short story, not a good thing. The things that cause an exception are device-specific, but are some common things. These are bus errors, executing an unknown instruction, division. Let's turn our attention now to device exceptions. What is an exception? Short story, not a good thing. The things that cause an exception are device-specific, but some common things are bus errors, executing an unknown instruction, division by zero, etc. RTOS has different built-in exception handling that allows a developer to catch and debug device exceptions. For this presentation, we're going to focus on the MCU devices. Here's a piece of code that will definitely cause an exception in the heartbeat function on line 68. RTOS allows the user to use 4 different types of exception handlers. First, there's the user supplied. Next is a RTOS spin loop, or a RTOS minimal decoding handler, and finally a RTOS enhanced decoding handler. These 4 slides will cover each one of these. And finally a RTOS enhanced decoding handler. The next 4 slides will cover each one of these in more detail. By supplying a function to the M3 HWI exception handler function parameter in the RTOS configuration file, the user can plug in their own exception handler. In the following example, the function myExceptionHandler gets a pointer to the exception stack and the link register. The developer can do whatever they want. For example, dump memory to flash LEDs, reset the device, etc. The benefits here are the developer is in charge. They can do whatever they want. The exception will still show up in ROV in the HWI module tab. There is no reliable decoding of the exception done, though, by RTOS for the user-supplied handler. If null is used instead for the exception handler function parameter, RTOS will plug in an infinite loop. If an exception occurs, the debugger will be in the infinite loop, as shown in the code snippet below. The exception still shows up in the decoding of the exception done by RTOS. The spin loop handler is the smallest footprint handler. If you'd like RTOS to decode the exception for you, you can set the enable exception parameter to false, and do not set the exception handler function from the previous slides at all. RTOS will plug in a minimal decoding handler. Now if an exception occurs, the decoded call stack will be in ROV. Additionally, there will be a minimal decoding of the exception sent to the CCS console, or wherever your system printf output goes. This handler is slightly larger than the spin loop, approximately 400 bytes bigger. Please note the quality of the backtrace is dependent on the device, the system compiler options that you have enabled or disabled, and the compiler toolchain. For the Cadillac of the exception handlers, a developer can set the enable exception parameter to true. Now, in addition to decoding the call stack in ROV, the handler will output a decoded exception to the CCS console, or wherever the system printf output is going. This handler is approximately 3K bytes larger than the spin loop handler. For this reason, we generally advocate using the minimal decoding handler from the previous slide instead of this one. And again, as the previous slide, please note the quality of the call stack is dependent upon the device, the compiler options you have enabled or disabled, and the compiler toolchain. In summary, RTOS offers 4 different ways to handle device exceptions: user-supplied handler, RTOS spin loop handler, RTOS minimal exception decoding handler, or finally RTOS enhanced exception decoding handler. If minimal footprint is important, use the spin loop. If decoding is important, use either the minimal or enhanced decoder. It's really up to the application developer to decide. Please note the exception hook function, which is available for the decoding handlers, will be described in more detail in the next slide. The exception hook function to either the minimal or enhanced decoding handlers. Note the exception hook function, which is available for the decoding handlers, will be described in more detail in the next slide. The exception hook function allows the user to plug in a function into either the minimal or enhanced decoding handlers. This allows the application to perform some action which they deem necessary as part of the exception handling. Please refer to the ti.sysbias.family.arm.m3.hwi module documentation for more details. Additionally, the website on the Processors Wiki ti.com site listed below has more extensive write-up about exception handling. Let's move our focus to memory management, or actually memory mismanagement. For applications that use dynamic memory allocation, here are some common mismanagement problems: overwriting the end of the allocated block, freeing the same block twice, memory leaks, and proper sizing of the heap. Using heap track in RTOS helps find these mismanagement issues. To enable heap track on the default system heap, simply enable it in the RTOS configuration file, shown here graphically or via a text file. Please note, RTOS replaces the C runtime malloc and free to use the default system heap in RTOS. When an allocation from the system heap occurs, if heap track is enabled, it increases the size request slightly and adds the following tracker structure to the end of the allocated block. Let's look at each field here. The scribble word is to help find overwriting issues. The QLM is a simple linked list to help keep track of the allocated block. The size field is the originally requested size. The tick field is used to identify when the block was allocated. And finally, the task handle is the task that allocated the block. Please note, you may have to slightly increase the size of the default system heap, since each allocation will be slightly larger. Let's see what heap track in ROV can help find. First, there's writing past the end of the block. When the target is halted, heap track in ROV shows which task allocated the blocks. For example, we see that my task allocated 2 blocks during startup. Note the tick is set to 0 for both of these, so we know it's during startup. And one of them has a corrupted scribble word. That's something that definitely needs to be fixed. Remember this for the lab later. Please note the boot task is used to denote any memory allocation that occurs during main or before. Heap track also might list an orphan task. An orphan task is a task that allocated memory but then either terminated or was deleted. Please note, this is not considered an error by heap track. Some developers like to have a single task do all the allocation and then terminate. However, it might be a cleanup problem by the developer also. The developer may have forgotten to free all the resources used by a task. By looking at the timestamps, we can help find memory leaks. For example, all the resources used by a task. By looking at the timestamps, we can help find memory leaks. For example, if we ran out of memory and when we looked at heap track and ROV and see there is an allocation occurring every 10 seconds, it should be pretty easy to find where the leak is at because we know the size, we know what interval it's occurring at, and we also know which task it's occurring in. Finally, heap track and ROV shows the peak or high water mark for the heap. This tells the size of the heap more accurately. Note, heap track and ROV shows a peak for when the tracker structure is added and when it is not added in. This allows the developer to know the size of the heap in case they want to disable heap track. If asserts are enabled in RTOS, heap track raises an error when a double free occurs. A double free is when the application tries to free the same memory more than once. Doing this generally messes up the heap and causes problems later which are a pain to find. Additionally, if an application writes past the end of the allocated block, the free will detect this and raise an error. Additionally, heap track offers some runtime APIs to print out tables of allocated blocks. Developers can print out the tables based on a task handle or from a specific heap. In summary, heap track can help you with finding and overwriting the end of an allocated buffer, freeing the same buffer twice, memory leaks, and help you properly size your heap. After the application is running smoothly, heap track can easily be disabled. We're almost at the end of this presentation. Let's summarize a few key points. Point 1. Please use ROV to help identify stack peaks. For a really simple single step, you can actually just run the bias scan for errors. This will search through all the modules and identify any problems, like blown stacks. Point 2. Turn on the minimal or enhanced exception handlers to help locate exceptions. Point 3. If you have memory allocation, enable heap track to help identify any memory mismanagement issues. Here are some key RTOS websites. We highly recommend customers use the forum. They will be working directly with a RTOS development engineer, and our goal is to respond within 1 business day. It also is a good resource to search for commonly asked questions. The RTOS online training will be getting some additional content this year, as we plan on adding driver presentations to go along with the current kernel slides. Also, we are actively updating the RTOS support wiki with any new issues found on the release versions of RTOS. Okay, the lecturing is over, so now let's actually start the lab. This lab will try to reinforce some of the concepts. As a reminder, the areas we talked about were stack overflows, exception, and memory mismanagement. We're going to use an MSP432 Launchpad for this lab. I picked this board because frankly, it was the closest one to me in my office. The techniques we learned are not specific to any device. I'm going to use CCS 6.1.2 and RTOS for MSP43X version 2.16.00.08. And finally, there are 3 exported CCS projects on the same website as this presentation. The application is more of a starter project. It has a simple console that spits characters out the UART and has support for 2 buttons. Here's the application's console's options. There's Help, which is H, C to clear the screen, M to display memory stats, P to print heap track stats, and R to restart the console. We had R in there because as we might grow this, we might want to shut down the console to go into low power modes. The 2 buttons are button 0 which increments a counter, and button 1, which prints out how many times button 0 was pushed. Please note all the system printf and printf output is routed to the console, the UART also. For this lab, you'll need some type of terminal application, like PuTTY or hyperterminal. CCS also includes a terminal application. First, you need to determine which COM port is being used. Please connect the USB cable to the MSP432 Launchpad's debug port and open the device manager to determine the COM port. It will be listed as the user UART. In the slide's example, it is COM27. Open the terminal window by selecting View, Other, and then select Terminal. Select the configuration icon on the terminal window and set the connection type to serial, and then the port to the value seen from the device manager. We used a baud rate of 9600 in this example. Note, we've seen some issues with CCS holding onto the COM port. Sometimes if the terminal session is not working, stop CCS, unplug the MSP432 Launchpad, plug the Launchpad back in, and then restart CCS. The simple application has 3 bugs in main.c. Play around with the console commands and the buttons on the board to see if you can find the issues and then fix them. The 3 exported CCS projects are the application with bugs with no debug turned on, the exact same application with debugging turned on in the RTOS configuration file, and finally the application with the bugs fixed. This slide shows how to import a CCS project. Here I selected the archive file, I've navigated to where I have the zip file, and then the 3 examples will show up. So then I can hit finish and those will get imported into my workspace. Please import the first application, the one with bugs and no debugging turned on. When you run the application, everything appears to be working fine. See if you can find the problems. I will let you know though, the 3 problems are kind of subtle, and they don't necessarily pop up without some of the debugging features turned on. So as kind of a refresher, you might want to check system and stack peaks in ROV, or you can just do a scan for errors in the BIOS module in ROV. You might want to enable some of the minimal or enhanced exception handling, and also you may want to enable heap track to see if there's any dynamic memory allocation problems. There's 2 different ways you can enable the debugging. One, you can go to the bottom of the TRTOS configuration file, also called the .cfg file, and you can start turning on things there. I've got them commented out at the bottom of the file. Or you can just import the debug example with bugs and debug enabled if you want to take a little bit of a shortcut. I will give you a couple hints about where the problems are at. I would say play with the buttons a lot. There's a bug in there, and there also is a bug in the console commands. If you play with those enough, you might see something pop up there. The next slides are actually going to talk about what the problems were and how we found them. So if you want to try to find them yourself and fix them yourself first, you better pause now, or if you just want to skip to the punchline and see what the problems were and how we found them with TR-RTOS, you can proceed. So I'm going to ramble here for a couple seconds. If you want to pause and try to solve it yourself, you can pause now. Otherwise, we're going to move on to the solutions. If you had used scan for errors in ROV before you had turned on any debugging features, you would have seen a strange message saying invalid task internal state. And you probably would have kind of scratched your head and said, well, what does that mean? But if we turned on the stack initialization and the runtime checking, you'd find that actually it's a stack overflow. And what's happening is the stack is corrupting some of the task state object. So once we turn those on, we see in the CCS, the output, or in ROV, we see that there was a stack overflow. So what we need to do is bump up the task stack size up to, we'll say, pick a K, 1024. This should be enough. And later, if we want to reduce this number once everything is working, we can look at ROV again and see what the peak is and adjust accordingly. The second bug is actually a memory leak. If you had selected M to see how much memory was free, and then R to reset the console, and then M again, you would see that there was a leak. But where is the memory leak occurring at? With heap track turned on, you would see that 40 bytes are being leaked every time we select an R. Please note, malloc grabs an extra 8 bytes, so when you request 32 bytes, you're actually going to get 8 more, which would be the 40. After a little looking, we can see the simple console function actually does not free the memory when 0 is returned, so the comment is wrong. We need to change this to be 1. So here, heap track showed us which task was having the memory leak, when was it occurring, and at what size the request was being leaked. So heap track really kind of gave us the exact area to look at. The final bug is if you hit the button 0 10 times or more, and then button 1 to print the count, you'll see in heap track that you're overflowing the buffer. This actually would have been really hard to find without heap track because you're just actually corrupting 1 additional byte here. So what's actually being overflowed here? So it looks like we're trying to allocate a buffer here that's the size of the string plus 2 for the digits, because we're only going to print up to 2 digits, and then there's a couple line feeds /ns. What we forgot actually is the string length does not return the length of the null terminations character. So this actually is wrong. We actually should have a +5 here instead of just a +4 to account for that null termination. Of course, in real coding, I would probably not pass this for code review because you hate stuff like this, just with numbers like this, and you probably even argue why are you allocating memory here. But we just want to show an example of a somewhat valid use case with a problem that would be really hard to find without heap track. So that was it. I hope you enjoyed the little techniques that you can use in RTOS to help find stack overflows, exceptions, and memory mismanagement issues. Take care.
Теперь то же самое прочитаем. Что-то я понял. Слишком мало. Берем. То же самое. Читаем. Как переводится. Что делать? Укрывает якость. Удобно. Включаем контроль. Я еще не включил, но вот пульс я уже нашел. Включаем режим отладки. Вот он. Короче, как вывод, что я понял. Я понял, что у нас есть три фигни, которые необходимо контролировать. Первую я знал, как контролировать. А вот exceptions постоянно валились. Стек, переполнение стека. Возникновение каких-то исключений, exceptions. И третье – это память, утечка памяти, превышение размера буферов и прочее. Сталкивался с этим один раз, но это обошлось. Вот, короче, если сейчас у меня в exceptions проблема. Если я научусь их видеть, контролировать, понимать, все, я найду причину, почему у меня валится. Хорошо, работаем. Угу. Угу. Пауза. Подключим контроллер. Так, я подключил контроллер. Сейчас там программа, которая моя полная версия весов с перекинутыми пинами на версию BSV9. И мы пробуем ее зашить. Давайте вот эту ерунду закроем сразу. Так, судя по всему, в память легло нормально. Ну что, попробуем стартануть, что ли? Давайте в тулсу для начала row classic вызовем. Так, вот она уже видит объекты, которые меня тут отлично. Отлично. Вот они объекты. Мы можем взять короче, пробуем стартануть. Все пошло. О, здесь у нас B20 нету. Может, поэтому она у меня клина ловит. GSM выход на связь. И, по-моему, у нас пипец. Все задачи зависли. Пауза. Так, тормозной ресурс в этом месте. Как бы нам это построить-то? Так, давайте-ка посмотрим задачи. Красного нету. Нету. Они мои задачи. Это у нас ядро. Stack size по килобайту эти комменты. Короче, ничего толком я тут не вижу. Мы это дело тормозим. Мы открываем более продвинутую штуку. Вы получился единица. Понятно. Так. Давайте мы это дело тормознем. Заново зафигачим. Вроде здесь все получилось. И, похоже, опять труба. Напрямую внутрь на предмет. Ух ты. Ну да, дата коллект сдохла. Если мы сейчас посмотрим, остановим, то коллект будет вращаться в спине. Не то. Тоже не то. Ладно. Датчиком температуры и внешнее питание. Думаю, что у меня аккумулятор просто просел, поэтому он не дает информацию. Сейчас посмотрим, там правда быстро не установится. Что-то вообще все мертво. Чем мертво-то? Питание все плохо, что ли? О, spin here. If my session has closed. Произошло какое-то исключение. Быстро падаем. Точно. Что, блядь, происходит? Не понимаю. Опа. Это. Что за чайная хрень какая-то? Все, устал, тупить начинаю капитально. Ничего не понимаю. Так. Сейчас мы это дело тормознем. Рассветнем. Если оно рассветнется, попробуем заново. Какая-то хрень. Тормознем, рассветнем. Отключим лишнее зарядное устройство. Попробуем заново. Ни хрена. Пауза. Зарядку. Убираем инструменты. Стартуем снова. Не помогает, все то же самое. Что, блядь, за исключение? Видите, меня не понимаю. Откуда ты сюда вылетаешь? Что у тебя происходит? И почему ты работаешь случайным образом, затыкаешься в разных местах? Ехали. Ну, диск прочитался нормально. Уже съемка завелась. И все, задачка зависла. Почему это коллег не выполняется? Так, вот это отключен. Доеду. Пауза. Что-то у нас сегодня с Максом тяжело до безобразия. Короче, попробуем. Так, reset, старт. И все валится. Я ожидал здесь увидеть что-нибудь, ничего не вижу. О, зеленка одна. Idle. Что это? сколько процентов. Начнем-ка мы со стека. Что это? Стек нарисовался. Ну, сканируется. Так, потом пойдем вот это хозяйство сверить с тем, что было. Но пока просто поработаем с этим, потому что сегодня очень неудачный вечер. Малой как резаный орет, что-то у него зуб, видать. Комп быстрый, шустрый. Супер. SSD-диск 1 терабайт. Эти вещи. Итак. Закрываем все эти вкладки. Они очень ресурсоемкие. Выходим из полноэкранного режима. Тут тоже закроем. Здесь стек usage. Запустим. И стартуем. Сам завелась, она должна пойти дальше, у меня задача стоит, не знаю почему. Сейчас дождемся, чтобы контроллер заругался. Все, заругался, пауза. Опять же, нет, не там. Ну, что мы здесь делаем? Селект, какой нахер, project селект. Вот он. Начинаю читать. Ай, не тормози. А, зачем извлечь нажал? Хорошо. Так. Вау. Это правильно. Блин, это не то, что я хотел увидеть. Так, это не то. Слушай, 102 килобайта задействовано. Не знаю, что это такое. И АЗУ 15 килобайт. Охренеть. Угу. Не вижу, где у меня стек. Не вываливаюсь нигде. Так, со стеком проблем нет. Странно. Очень херово поймет. Тоже не понимаю, что он от меня хочет. Пылится, ругается на что-то. Exceptions. Твоя мать, как эти exceptions работать? Не понимаю. На сегодня все. Всем привет.